So we're starting a new unit. We're still talking about physics, though. We're going to start with talking about my least favorite Winter Olympic sport. So you have to think back. Was it last year or 2 years ago? Last year, Winter Olympics happened? Okay, so any guesses? Any predictions? Ms. Carbling's least favorite Winter Olympic sport. How well do you know me? It's only, it's been a trimester. You've seen me for a trimester. You've interacted with me that long. What do you think? Oh, it's not cross-country skiing, but I don't watch cross-country skiing on a regular basis. That's a good guess. That is not the guess that most people usually guess first. So that's interesting. It isn't.
No.
What?
It's a sport called curling.
There is totally a sport called curling. I love curling. I love curling. That's the thing that everybody guesses. Everybody always guesses that I dislike curling the most. But secret information, I love curling. I think it's so cool. There is so much physics in curling. If you've never watched curling, I totally recommend it. It's all about friction, and it's all about interactions between objects. Yeah, they scrub the ice so that they get it really, really, like you can get it either really, really smooth or really, really rough to get it to slow down or speed up. They have these big stones. It's awesome. Strongly recommend it. It's kind of like an ice version of shuffleboard. Yeah. Not my favorite Winter Olympic sport. Anybody else have another guess?
What's that last one called? The cart.
Like bobsled?
Yeah.
Bobsled is awesome. Yeah, I mean that's all physics stuff too. Yeah. I mean all of the Winter Olympic sports really are physics. But yeah.
Speed skating?
No, but that's an interesting guess. You're on the right track, I guess, but not quite. I do like speed skating. It's kind of intense, right? Yeah. That's intense. Yeah.
Hockey.
I like hockey. No.
Like the one where they skate and have to shoot at targets.
Oh, what is that called? Is that the biathlon or something? Yeah, I can't. That's not what it is. Yeah, these are all really good guesses. I like it. Yeah, snowboarding's awesome to watch. Man, that's so cool. Now, my least favorite Winter Olympic sport. A lot of people don't even know that it's a sport. Ice dancing. Does she? Now, every time that I say this, I'm always afraid that I'm going to offend somebody. So I don't want to offend your mom. And to be clear, I could never be an ice dancer, right? So I'm not like, that's not a sport because blah, blah. I just mean that it's really, really sappy.
It's just hard.
Okay?
Will you pull the videos?
I'm going to describe it for you today. Okay. So I like to watch figure skating. I think it's interesting. It's just kind of, they dance and they jump and they, like in partners figure skating, they can throw each other. Like that's pretty exciting. There's intrigue in that, right? Like, are they going to throw one of them and they just like, who knows, whatever. The trouble with ice dancing, in my opinion, and maybe I don't understand it completely, but this is my understanding, is that in ice dancing, it's a partner sport. And both partners have to have at least one skate on the ice at all times. So the trouble with that is that there is no jumping. And there is no throwing of people. And those are the exciting things to me. Like, that's why I like figure skating. But ice dancing, it's just a lot more sappy. So they wear, like, these big costumes. And it's very, very lovey-dovey. I don't really like that. It's kind of like, I like a good romantic comedy now and then, I suppose, but like romantic movies, like, no, thank you. It's not my thing, okay? So the reason that ice dancing drives me absolutely bananas is because 98% of all ice dancing shows, and maybe I'm exaggerating, I don't know, I haven't watched and tallied, but it seems to me that about 98% of all ice dancing shows start in the exact same way. Okay. Now, the really annoying part is that it starts like this. Ben, come here for a second. Have you ever done ice dancing?
Yeah.
Have you? He's like, actually, I'm planning to go to so-and-so and win the gold next year. No. Okay. So this is how ice dancing works. I picked you on purpose. Okay. So there are two ice dancers. Okay. And they wear all these fancy costumes. 98% of all of the ice dancing routines start in the same way. Okay. Just like this. I'm a little short. There you go. You don't have to be short. You can be tall. All right. And so the music starts. Are you with me there? And again, the romance, like, I'm not into that. But it's this thing. You hold your position. Come on now. Yeah. And they gaze into each other's eyes. And then what do they do when the music starts? What happens?
You break apart.
They push off. Okay? So the only good thing about ice dancing, you can sit down now, because now we have this image in our head.
Okay.
It was very nice. Thank you for doing that. The thing that is, the only good thing about ice dancing is that very moment. After the gazing into each other's eyes stuff, okay? And before the rest of the dancing, there's a little good physics in there. And that's the only part I really like. And so here we have, so we've got these two people, right? We've got, I'm gonna do a little bit of, we're just gonna tell a story here. So when I was young, and I don't know if this is still true because I don't watch ice dancing on a regular basis anymore, but when I was young, Russia, the Soviet Union, right, was very, very good at like all ice skating and ice dancing sports, okay? So I'm going to tell you the story of two ice dancers. We'll call them Alice and Boris. Okay? So Alice and Boris, we can imagine them standing there, and the music starts. And there's all that eye-gazing stuff. And then they push, right? And the one good moment of the entire show is that push. Because as a physics teacher, I'm saying that push is really a what? It's a force, right? So my question for you is, who's pushing on whom? Who's pushing on whom? That's what I really want to get to. So I've got Alice. I'm going to draw, here's Alice. And here's Boris. Now let's start before the music starts, when the eye-gazing business is happening. Tell me the forces that are acting on Alice.
Force of the earth.
Force of the earth! Which one is that one, pulling or pushing? Down, right? Yeah, the force of the earth is pushing down. The force of the earth on Alice. What else is pulling or pushing on Alice? Before the music starts? FN. FN? The force of the what? So we're talking about objects. The surface, right? The force of the surface. And in this case, that's the ice, right? On Alice. And how do the force of the ice and the force of the earth compare? They're equal in magnitude, right? So they add up to 0. Tell me about the forces acting on Boris. Same? Force of the earth on Boris. Force of the ice on Boris. How do the two forces on Boris compare to one another? This isn't a trick question, friends. You know the answer.
They're equal.
They're equal. How do you know they're equal?
Well, they're equal.
Because he's not what?
Moving.
Not moving, which means he's not accelerating. Okay. He's not allowed to talk anymore. You guys have to say these things. Don't rely on that one. He's loud sometimes. All right. Now, question for you. How does this force of the earth compare to this force of the earth? Force of the earth on Alice versus force of the earth on Boris.
Probably. Unless they were.
They're different probably. Say that a little louder.
They're different probably. Unless
They have the same mass.
Unless they have the same mass. Does that make sense? So we're making an assumption, okay? I set this problem up on purpose in that way because we're going to assume that who has a bigger mass? We're going to assume that. Now, it might not be true, and I want to make that really clear, right? We don't know that for sure, but for the purposes of this, I'm just going to write this down. I'm going to let us go with that assumption that the mass of Alice is less than the mass of Boris. Just for the purposes of this project. So to make sure that we understand then, that means the force of the Earth on Alice is is smaller than the force of the Earth on Boris. How do the forces of the ice compare? What's that? Boris's is bigger. Why? These guys have to be the same. Are you with me there? F-net equation. We could write it out, right? Fn, negative Fg has to add up to 0. If this one's bigger than this one, then this one's got to be bigger too. Is that okay? You say, why are we doing this? We did this all last time, right? All last unit, all last trimester. What are we doing? Because I want to make sure that this part makes sense. So now the music starts, right? So here we go. So here are Alice's hands, and here are Boris's hands. Oops, they need to come a little closer. We'll make them really wide hands. Wow, those are really, there we go. Okay. The music starts, and they push off. Who pushes? They both push, don't they? Yeah, they both push. It's kind of weird to think about it, but they do. They both push. So then once the music starts, we can add some forces here. So I'm going to add a force here. This is the force of who on whom? This one here. It's the force of Alice on Boris. And here we've got the force of Boris on Alice. So we've got two applied forces. Okay. The free body diagram of Alice just has 3 forces. The free body diagram of Boris has 3 forces. Okay. Those are the 2 forces that we've just introduced. I've got a few questions for you about those forces. First question, question number 1. Who pushes first?
Is it a trick question or is somebody actually going first?
It's a question. It's a useful question for you, especially if you have siblings. Okay? It's a useful question. Who pushes first? I'm going to push Leanne, is that okay? I'm going to push Leanne. When I push her, I apply a force to her, right? Does she apply a force to me?
Yeah.
She does. Do I push her first? Does she push me first? Who pushes first? No one does. Are you with me there? Yeah. Nobody pushes first. The force happens at what?
Same time.
The same time. Yeah. Who pushes first? Nobody. Okay. The forces appear. The forces come into being at the same time. This is helpful if you have siblings, right? I'm imagining younger siblings, but sometimes high school kids are kind of immature too, right? Mom, he pushed me. Well, she pushed me first. Is that true? Who pushed me first? No. She pushed me at the same time that I pushed her. Right? Yeah. Yeah. Nobody pushed first. The forces appear at exactly the same time. Question number 2. Who pushes longer? How long does a force last? If I push on a chair, when does that force end?
As soon as the chair comes out of contact.
Right. When there's no more contact. They're all contact forces, right? So I'm pushing, not pushing anymore. As soon as that chair leaves my hand, I am no longer pushing. Okay? When do they start pushing? Yes. When contact happens, forces happen. And when contact is broken, forces are broken. So who pushes longer? Nobody, right? Okay. Force lasts as long, as the contact lasts. Okay, question 3. This one's the weird one. They gaze into each other's eyes. They're both on skates, and that's important, right? They're on skates on the ice. Why is that important for me as a physicist doing this problem? What doesn't exist? If Ben came up here and we did this again and we turned on some really cheesy, bad music, right, and then we pushed, what's going to happen to us?
There's no friction. Well, there is friction.
There's no friction.
There's friction here, right? On ice, very, very little friction, right? Yeah, they've just driven the Zamboni over this entire thing, so it's now nice and super smooth, okay? And so when we stand there and we push, okay, we push at the same time for the same amount of time. I want you to imagine what's going to happen. Okay, so if we all get dressed fancy and then we do this pushing, my question for you, this is the one that I really, really care about, is who pushes harder? Or another way to say that is who applies more force? So Ben, I'm going to have you come over and talk with Ryan and Matt, and I want to have you come over and talk to these young ladies. I'd like you to have a conversation real quick to answer question 3. Have that conversation right now. Who pushes harder? Who applies more force? Is it Alice or Boris? And not only do I want you to answer the question, I want you to come up with a reason for your answer. Go ahead. Discuss. You guys have to talk. I'm going to wait. Have a conversation. Talk about your gut feeling. Who do you think is going to push harder? Who pushes harder? Maybe think about what's going to happen to Alice and what's going to happen to Boris. Remember, we've made this assumption that Alice is smaller than Boris, right? They're not the same mass. Boris is very big. Alice is small. Who's going to push harder?
Is that a trick question?
I never ask you a trick question. I only ask you questions. I ask you physics questions because I want to see if you understand. And this one we don't know I have not told you the answer to this question. But I want you to figure it out.
That's volatile.
See, that's why I think
Are you ready or not quite yet? I like thinking. I like the fact that you're thinking. It makes me happy. All right. Matt, will you get us started?
We said no one.
You said no one. What was your evidence for that?
Well, ice has such little friction. They both push equally. They're going to move.
So if Ben comes up here and does this with me right now, no, and I love this. This is what I'm at. So I'm trying to extrapolate. I'm not trying to prove you wrong. Does that make sense? I'm trying to make sure that I understand your reasoning. So if Ben comes up here and we do this thing and we push, right? He's going to apply a force to me.
Yeah.
I'm going to apply a force to him. Which one of us is going to push harder? What'd you guys say?
Oh, actually, we're sort of like we don't.
Tell me what your gut feeling says.
Personally,
Tell me about it. Tell me about your gut feeling. What was your gut feeling?
I think that neither.
Why?
Well, like, I just don't feel like the mass can affect that because I don't know because you determining how much you like push like, on someone. Yeah, someone can push harder, but in that situation, I don't like it. Sort of determines on how each individual pushes, right? Because one person could push harder in a certain situation.
Can they? What situation?
Like, if I don't know, like if the guy pushes harder, like one time, but then the girl pushes harder the other time, can't like they change how hard they push?
That's what I'm asking.
No, I don't know.
Put your hand up with your partner, and if you have a trio, then do some sort of like triangle thing. Put your hand up with your partner and push on it. Push on your partner's hand. Okay. If your partner pushes harder, what are you doing also?
Pushing harder.
You're pushing harder, right? Can your partner push harder than you and apply that force? Is it possible? Go.
Depends on the mass.
Depends on the mass. Why?
So Alice will have to apply a larger force to move Boris because quite the mass. They want to move the same distance.
Do they move the same distance though?
Well, I don't know, but it doesn't say anything.
It doesn't say anything about that. Let's talk about that part because I think that's going to help us get to where you were going, Josie. But let's talk about that. Once they push off, let's ignore the forces for a minute. What actually happens to Alice? Imagine this. You guys have seen this. You can picture what's going on here, right? What's going to happen to Alice? Where's she going to go? Yeah, look at her forces, right? Her net force is going in this direction. She's going to go that way, right? No friction. So, woo, there she goes. What's going to happen to Boris? He's going to go backwards also, right? How does Alice's motion compare to Boris's motion? What do you imagine happening?
Depends on the force and then he goes like.
Yeah.
He doesn't move like that much.
Well, he's going to move, but he's going to move much more quickly or slowly? More slowly, right? So let's talk about this. You remember that we said that the result of a force, or I should say a net force, write that. Of a F net doesn't equal 0. The result of a net force that doesn't equal 0 is what? What's going to happen to the object? Come on, friends. It's going to accelerate, right? It means the acceleration does not equal 0. We know that acceleration is equal to F net over m. Tell me about Alice's acceleration as we compare it to Boris's acceleration. Who has a bigger acceleration? Alice, why do you say that?
Is it her mass?
Well, that is, yes. You're answering the other question that I was going to ask next. It's like you're channeling my understanding. Yes. So I think she is going to accelerate more. I think that the acceleration of Alice is going to be greater than the acceleration of Boris. My evidence for that, and then I'm going to get to what you were just saying. Is that okay? Acceleration, you guys, is just change in velocity over time, right? What's their initial velocity? They're standing there gazing into each other's eyes.
0 meters per second.
0 meters per second, he says. Do you guys agree with him? What's their velocity after? Is it something else?
Yes.
Yes. And if the velocity of Alice after is higher than the velocity of Boris after, and they both interacted for the same amount of time, that means that Alice's acceleration is bigger than Boris's acceleration. Jordan, you look unhappy with that statement.
But after they're not touching each other.
There's no more acceleration.
Yeah.
Correct. When I like it because they're on ice, so that we don't have to worry about any slowing down. Yeah. So Boris is just going to go back slowly. Alice is going to go back slowly or fast, and she's either going to, quickly turn and do something fancy, or she'll run into the wall. Right? Hopefully she doesn't run into the wall. That would be unfortunate. I think you would not earn a gold medal that way. Right? Okay? But she's going to accelerate much more quickly than he does. Is it because they have a bigger force, though? Or is it because they have a smaller mass? Does that make sense? Alice has a smaller mass, so given the same force, Josie's intuition was right, given the same force, a smaller mass is going to give you a bigger acceleration. With me there? Given the same force, the acceleration is going to be bigger. The force of Boris on Alice is equal to the force of Alice on Boris. Okay? Those two forces are exactly the same. Who pushes harder? Nobody pushes harder. Now be careful, my friends, because I think that you answered no one because you kind of followed the pattern. Okay? But I think that if I had asked you that question at the beginning of the day, what's your inclination going to be? Who pushes harder? Who's able to push harder?
Boris.
Alice or Boris? Boris, right? Yeah, he's got lots of muscles, right? Like that's what our brain tells us, right? That Boris can push harder. Probably I'll ask that question tomorrow. I want to make sure that you're thinking about it and that you know that any interaction, any force is an interaction between two people, right, or two things. And that force is the same between those two objects. The force of B on A is the same as the force of A on B. I'm going to take that one step further in just a second, but I want to write this down. So who pushes harder? Nobody. F of B on A is equal to the force of A on B. Statement number 4 is who accelerates faster. And what's the answer to that question? We're going to say Alice. Why? So what did you say, Stella? Yes, she has a smaller mass. Okay. All right. Question for you. Let's make sure this is making sense. Frog? Yeah. Once I let him go, I want you to tell me the free body diagram on him. What does this free body diagram look like as he's falling? Just gravity. So here's the frog. The only force pulling on him is which way?
Down.
Down. The force of the earth on the frog. My question for you. Does the frog pull on the earth? Yeah. So if I draw the earth down here, the frog pulls on the earth, right? Which way does the frog pull on the earth? Up. Force of the frog on the earth. What's that?
Why is it down there?
Because this is the free body diagram of the earth.
Oh, of the earth.
Yeah,
Of the earth.
that's a
Okay.
big question. Did you guys catch what he asked? Because that was not a trivial question. This arrow is a force of the earth on the frog. All of the arrows on the frog come from the frog. This is a force of the frog on the earth. So this is part of the free body diagram of the earth.
Okay.
Is that okay?
Yeah.
Okay. Who pulls first, the frog or the earth? Same time. Who pulls harder, the frog or the earth? Watch. Watch it. Who pulls harder, the frog on the earth or the earth on the frog?
We did.
Who pulls harder? No one. But Stella does not like that. Why don't you like that?
And the frog goes down.
The frog goes down, doesn't he? For sure. We know that when this happens, the frog is going to accelerate, right? We even know how fast the frog accelerates, don't we? We studied that a long time ago. We know that the acceleration of the frog is negative 9.8 meters per second squared, don't we? But do you want to know what's weird, friends? The earth accelerates too. Is it very much though? No. Because remember, acceleration is equal to F net over M. Who has a bigger mass? The earth or the frog? A little bit, right? A little bit bigger? A little bit bigger mass means a little bit smaller acceleration. Okay? It's weird to think about, but the force of the earth on the frog and the force of the frog on the earth are equal. They have the same force acting. That's weird. We need to write that down. That's weird. Force of the earth on the frog is equal to the force of the frog on the earth. That's not what our brains want to tell us. And that's because the accelerations are different. The accelerations are different. That's what we see. We see the acceleration. We don't see the force. We see the acceleration. That's the thing that changes. Yeah.
Is there a way you can calculate how far the Earth moves from that?
The acceleration of the Earth?
Yeah.
Absolutely there is. Yes. We will do that, not today because the bell's going to ring in just a minute. Like right there. Whoa. But we will do it later. Yeah. Yeah. All right, you guys, I will see you tomorrow. It might be a little bit